Now it's a pleasure to introduce our next speaker, Professor Harald Andrés Helfgott from Georg August University of Göttingen and Institut de Mathématiques de Jussieu. And the title of his talk is Better Bounds on Growth and Diameter in Classical Chevalier Groups. Please, you may share your presentation. Check microphone. We don't hear you.
Can you hear me now?
Yes, yes.
Can you hear me well? I also have a microphone that might help.
Yes, yes, we hear you.
Okay, well then. And now you can see my screen, right?
Right.
All right. So in the end, I chose a slightly different title because if I start my title with better, it sounds like I am selling something. But it's a pleasure and an honor to be invited to this conference. And our thoughts are with Ukraine in these difficult times. So very well. So let me define some basic terms first. I'm sure some of you know these better than I do. I'm really from number theory, but given a group generated by a set A, we can define the Cayley graph. The Cayley graph consists of vertices and edges. The vertices are the elements of G. And then the edges, what you do is you join any element G with any element of the form A times G, where A is any element of the set of generators A. All right, so I have drawn one edge. Of course, there are lots of edges. So first of all, this graph is connected. You can easily see that from the fact that, from the assumption that A generates a group. And this graph is also symmetric, that is, every edge goes both ways. If it is the case that for every element of the set of generators, the inverse is also in that set A. And we will assume that. It simplifies matters and it doesn't change the final estimates much. All right, so the diameter of a graph is the following. So first you define the distance between two, so you define the length of a path to be the number of edges in the path. So every edge is taken to be of length 1, even if it looks bigger. Then the distance between two elements is the length of the shortest path. It's the usual definition of distance, whether you take the Euclidean distance or you're working on the planet surface, or whether you are in a city and you want to know whether it takes a lot of time to get from one point to another. And the diameter of the graph is the maximum over all pairs of vertices of that distance, that length of the shortest path. So if you take as a city, the diameter of the city is, you take the worst choice of 2 points and you see how long it takes you to get from one to the other. All right, so it's nice when the diameter of a group is small. It's a simple exercise to see the diameter without using, for a Cayley graph, without using any graph theoretical concepts, because you can also say, by definition, any element of the group can be written as a product of elements of A, because A generates G, and you define the diameter to be the smallest case such that every element of G can be written as a product of length at most K, right? So the diameter is small if you can write every element of the group as a short product of the generators. And we may further define the following, and this is not so standard annotation, though other people use it. You may define the diameter of a group to be the worst case diameter, the diameter for the worst set of generators, the set of generators that makes the diameter the largest. Right, and you might think that for many groups there could be really bad set of generators. You're letting the devil choose your set of generators. But in fact, there is a conjecture based in part in previous folklore by Babai that says that for every group, every finite simple group that is not abelian, the diameter is really quite small. It's almost the logarithm of g to some unspecified power, an absolute constant. It's known that c has to be at least 2, but we don't actually know how large it is. But if you prove this with c equal a million, people will admire you, even if it's a million to a million. Well, for which cases? So, I mean, if you prove it for all finite simple non-abelian groups, it used to be the case that this was not known for any families of groups. I mean, this makes sense. It's a question only when you consider infinitely many groups. You consider a family of groups, and you want to prove it at least for a family of groups. So I proved this back in the day when G is SL2 over Z mod PZ. This was generalized to SL2 over a finite field by two young people independently by deny and value. And then I generalized this to SL3FP that already took a lot of work. And much of the SL3 paper is actually about more general groups. So the tools are developed more generally, and together with my postdoc at the time, we managed to get make some headway towards SLN and SON, but eventually the statement was really generalized to all groups of Lie type of bounded rank by two teams of people, Piver, Szabo, and Bruyère-Green-Tao. And sometime later, well, you know, all finite simple groups that are not abelian fall into three classes. So you have, well, you have the monster and things like that, but there are finitely many of those, so you don't care about them in this sort of asymptotic statement. So forget about array groups. Well, the groups of the finite group, the groups of Lie type, the finite groups of Lie type, and those are covered. And then you have the alternating group. So for the alternating group. And so this is what we know about all of these families. So you might think that we know everything. Well, almost everything, in the sense that here, in the case of the symmetric group, we don't quite have a constant in the exponent. We have something that grows slowly. Well, but it's also the case that the situation for linear algebraic groups is not really that satisfactory, in the sense that what does bounded rank mean? Bounded by what? Well, bounded rank is just people's way of saying you don't get an absolute constant C, you get a constant that depends on the rank of the group. And it depends, it used to depend. How badly? So the rank, I mean, it's not so far from n. As in the rank is n-1 in the case of SLN and so forth, right? In the case of SO2n, it's n and so forth. But so people have really this bound that looks like Baba's conjecture, but the constant depends on the rank. And how badly does it depend on the rank? So in Piver-Szabo, it's an exponential tower. So it's e to the e to the e to the e to, and the number of e's depends on r. In fact, it's linear on r, if I remember. And in the case of, they don't give any bound on CR. They can't without changing their language. They use ultrafilters, so non-standard analysis. I guess if you tertiary their proof enough, you would make it into something that gives you CR, but then it would be a proof that is close to Piver-Szabo and gives you a bound that is basically Piver-Szabo, unless you start having new ideas to put in, and in which case you might as well work with Piver-Szabo as your basis. So can you do better than this? I mean, exponential towers make people unhappy. So our main theorem, and by the way, I should make clear this is joint work now in Budapest, and my former postdoc is in Rabbi Pai. So what we have proved is indeed that the diameter of G is bounded by log of G to a power that is polynomial on the rank. So not an exponential power, just a polynomial. In fact, basically just r to the fourth. And the constant isn't even obscene. It's something very reasonable. All right, so what are the ideas of the proof? Yeah, not going to be let off lightly. Let's talk about proofs. So there are basically two elements, two main stages in a proof of this kind. I mean, all of these proofs for linear algebraic groups fall into one family, they all, even though people have worked on it separately in some cases, they all can be put in a very clear scheme. Where, first of all, you have dimensional estimates, which are interesting in themselves. What do I mean by a dimensional estimate? I mean, you have a set of generators of G of K, and via variety, any variety, really, nowadays, and you can prove that the intersection, you can prove basically, if you read this statement, how you should be reading it is, so here A to the K is just a product of the set of products of at most K elements of A, not necessarily distinct. So how should you read this statement? Well, you can just read it. It's not very complicated. But it basically says either A to the C2 is much larger than A. So remember, bars means the number of elements. So either A is growing rapidly, A being any set of generators, or its intersection with your favorite variety, you get to choose whatever variety you want, is not larger than you would naively expect. Namely, it's not larger than A to the power dimension of V over dimension of G, right? So you can see it as follows. Either a completely arbitrary set of generators, either it grows rapidly when you multiply it by itself, or when I have this, it's like a ball, or it's roughly like a ball in the sense that you have this three-dimensional object, and if I stab it with something one-dimensional, then my intersection will not be of size greater than cube root of my ball. So yeah, you can see this interplay between it's either growth or my set is geometrically rather beautiful, to the extent that stabbing is beautiful, but well, behaves beautifully under stabbing. Or you can do the same with a curve. I mean, the bound will degrade a bit, of course. Constants will depend on the degree, but still, or a surface. All right, so this is a kind of results with a bit of history. The first results of this kind that I'm aware of date to Larsen Pink, but they were not working with, say, a set of generators. For them, A was a subgroup, a quote-unquote sufficiently generic subgroup of G of K. So, of course, not a set of generators, but just a subgroup. So what was their deal? It's interesting that in much of this field, something that comes into play are tools that were developed in the 80s and 90s, when people were just, learning to live with the classification of finite simple groups. It has become a socially accepted fact, the proof, but well, it's larger than any encyclopedia, and it's not actually all written down, or it wasn't. So people were and are still trying to replace some parts of the classification or of things that can be proved with the classification with things that don't depend on the classification. So they were actually classifying subgroups of SLN, and they were showing either your subgroup is pretty much algebraic or it has this funny property. Generic would mean the opposite of being contained in an algebraic group here. All right. So that looks like a relative, really, of these dimensional estimates. When I was working already in 2005, I was working with a general set A, and originally in SL2 and then in other groups, SLN, SON, etc. But I was working with fairly specific varieties, one at a time. We will later see how that's not so stupid, but it did limit me a little. I was doing things a bit by hand, and I was obtaining estimates that were clearly of this form. Then Khrushchevsky, actually Larsen and Pink's paper was a draft for a very long time. And Khrushchevsky and Pillai gave cleaner versions using model theory, versions that really looked like this, at least for A subgroup, but also for A set, because, well, they were also aware of this work. And then in certain circumstances, at the very least. And then Piver and Szabo and BGT, what they did was based on, well, my work, but also Larsen Pink's, as interpreted by Hrushevsky and Hrushevsky-Pillai, they got really dimensional estimates that were fully general, right? So of course, C1 and C2 will depend on the degree and the dimension of G, but in all of these, they don't depend on the ground field. Otherwise, there's no joke, right? They don't depend on the ground field, okay. But the question is, how do these constants depend on the rank of G, the degree of V, and the dimension of V? And in the work of Piver-Szabo and Briard-Gintau, which is very pleasingly general and powerful, the dependency is actually very poor. And that's why the final bounds are very poor. The dependency on the rank is very poor. Now, there's a second stage to the proof, and that's when you have a dimensional bound for non-maximal tori, but you also have a lower bound. So the intersection of this thing with the pencil is at least constant times cube root for maximal tori, but that by a variant of the orbit stabilizer theorem, that actually follows from an upper bound. So for a regular upper bound dimensional estimate for the variety, which is a closure of the conjugacy class of a regular semi-simple element. All right, so given those two dimensional estimates, pivoting, it's an inductive, yeah, you can call it an inductive procedure that gives you that either A grows rapidly under multiplication, K prime here is a constant, or A to that constant is already an entire group. Right. So in other case, you are done. Either you got the entire group or you got growth, which is great because you can repeat that and repeat. Right. So the original proofs. So pivoting, we will not talk so much about. The original proofs for SL2 and SL3 use the sum product theorem by Bourgain and Bourgain-Katz-Tau. It's really Bourgain's part, which is also in his separate papers, which is really important here. But then, yeah, you could live just with that. But then it became clear to me that you had to abstract the idea in pivoting. I didn't have quite the right sort of abstraction, or I had something that was useful for solvable groups, but then the right abstraction of pivoting or the right usage of pivoting for G, it can really be found in Piver-Szabo and Briard-Gintau. And what is this pivoting? It's really induction on a group G. You might think that induction depends on an ordering, that it requires an ordering, but it's not that way. You can just work with a set of generators, A of G, and you can do induction using that. All right, so we will improve both, but I think I'll focus entirely on improvements in one, because that is already interesting. Well, it's not just interesting, it's the most interesting part, but also enough to give us bounds of the form that we want to prove. And there are two stages here. First, how to improve general dimensional estimates, and how to improve dimensional estimates specifically for the varieties that we want. Well, doesn't that risk being a bit ad hoc? Well, you have to think a little. You have to say, in a way, it's a throwback to the days when I was working with particular varieties, but including these in a certain sense, at least the torus. But you have to think, what makes the conjugacy class of an element spatial or a torus spatial? Well, the torus is a group, an abelian group, an abelian algebraic group. And the conjugacy class is an orbit, and we will use that in a little while. That will allow us to get much better dimensional estimates for those varieties, which are really important for us. So what sort of improvements? So the first stage, you could say that it's a sort of thing that people suspect you're doing when you're doing explicit, or you're improving explicit bounds, namely, you're going to the basics of the field and you're making them explicit if they aren't already, and you're trying to improve the constants there, the dependency. I don't really care about 891, I just mean the dependency on things. So, you take a basic textbook in algebraic geometry, such as Mumford's Red Book, and you have some statements there that, I mean, they are older, of course. I think at least one of them is due to Chevalier, some other mythical hero of the past. And then you have that, for instance, if you have a variety and you have a morphism, then you want to be able to bound the degree of the image well. If you have, or the degree of the inverse image, right? Basic things like that, but also the following thing, which is due to Chevalier, I'm pretty sure. Textbooks in algebraic geometry rarely mention the heroes. Then you have a variety, you have a map, a morphism from the variety to some other affine space, and you consider the difference in the dimensions, the dimension of the domain minus the dimension of the closure of the image. And there you have that generically for a point like that, not a point outside a variety of smaller codimension, outside an exceptional variety, the dimension of the preimage of the point will be exactly U. All the components will be of dimension U. And the exception will be some sort of variety of lower dimension, a variety Z. But we want to bound the degree of Z and bound it well. Well, we had to learn how to do these things. Sometimes Math Overflow really had people giving us good ideas. The basic way to do this well rather than badly is to cut things with planes as much as you can and then project, do other linear things. Linearity is your friend. Well, that's as basic as yeah, everybody, it's obvious in retrospect and everybody should do that. Linear things are good. And you have to get a bit clever about using it. And that's already good enough to avoid the exponential power syndrome, because you get a bound like this, which looks horrible, but compared to an exponential power tower, it's wonderful. All right, otherwise keeping the Larsen-Pink argument. But let us go further. We are not satisfied with that. So let me first give an improvement on escape from subvarieties. Well, first I have to explain what escape from subvarieties is. What is escape? So Jason, I understand, had something to do with Ukraine, but in his later adventures, he ended up in Crete and had to do with a labyrinth. So Jason has to escape from a labyrinth. So the labyrinth is a variety. And what you're given is that you have a set of generators for your group. You have a variety. You are stuck in this variety, but you are told, you're a point stuck in the variety. You are told there exists a way out of this variety. So the orbit of A to X is not contained in V. There's some product of elements of A that gets you out of V. And then the wonderful escape result tells you that there exists a short way, a short product of elements of A that gets you out of V. Well, how short? So before, and this is not new to me, this is an old argument. You can find it in Eskin-Moses O, for instance, which is roughly contemporary with my first paper, but the argument may be even older. The old argument gives you that K is at most D is the degree. So D is the degree of V, and D is the dimension of V. And you get that K is at most big D to the 2 to the little d, which is not fantastic, but it's okay. And the idea of the proof is basically induction plus Bezout. You are in this variety, you are here. Oh my God, am I ever going to get out of this? Well, the variety cannot really be invariant under the orbit, otherwise you could not very well get out of it. So you consider this and the variety times some generator that does shift it. It has to exist. And now maybe this other variety also contains you, but then you are only trapped in the intersection of these two varieties. And as soon as you get out of that intersection, you are basically free to go. One more step. yeah, so this was used in my first papers. It sort of disappears in Georgian town papers, so that's because it's subsumed into the Larsen-Pink argument there. But now I don't subsume it, and one can give it a much better bound. And I'm actually very, very glad to say that it was my student at the time, Daniele, who is a co-author, who, well, that has done many things, but in particular, he came up with the argument that gives you this much improved bound. So yeah, just compare this to this, it's much better. And how do you do it? Well, in induction, you are generally keeping track of a quantity. It can be the degree of something, but in our case, we don't want to keep track of a degree as people used to do. We want to define the right quantity to keep track of. And once you define the right quantity, the new bound basically proves itself. Well, except for a tricky part, but think where you have to curse invariant components, but we will later see how cursing invariant components is a wonderful thing. But this new argument is enough to give you the dimensional bounds with C2 here replaced by big D to the dimension of G squared. Right. That's already very good. But moreover, you can also get a better inductive, better inductive procedure than Larsen-Pink, because Larsen and Pink do a complicated double induction. But if you uncomplicate it, if you choose a different inductive procedure where you're really trying to go down in dimension all the time, then you get much more reasonable bounds. Right. And all of these suffices to give you a diameter bound where in the exponent, the exponent here is already polynomial on R, but you have a constant in front, which is doubly exponential. Right, so singly exponential would be good. It already just give you R to the C, but this is doubly exponential, and that's a problem. That's not what we want. Maybe we should have already published at that point, and that actually, those dimension estimates will become are becoming a separate paper in the fellowship of a friend, but that's as far as we can go with our improvements to general dimensional bounds. Now, I've still got a little bit of time, right?
Yes.
Okay.
You have 10 minutes, even more.
Excellent. That's enough. Now, let us try to go further than those bounds. So we've got pretty far for general dimensional bounds, but let us try to go further. A second improvement to the escape procedure. So if you can try to prove a statement like this from the escape procedure, but you get rather bad constants, but then you realize that by this point we have refined the proof enough that we need to really just improve it a little bit more to prove a much stronger statement, or at least a much more flexible, a much more powerful statement. So you still have the same situation. Theseus is in the labyrinth, in the variety. Now, Theseus is very courageous. He got all the way to Ukraine, starting from Greece in a dinky little boat, and then had to deal with all sorts of monsters. But then when he got to Crete, yeah, I think Theseus was actually not that smart. He always needed somebody to help him. Oh, I'm confusing Jason and Theseus. Before we had Jason, now we have Theseus. Jason was in Ukraine, Theseus was in Crete. Now Theseus, maybe Jason was smart, but Theseus was being held by a different woman. So Theseus was being held by Ariadne. So Theseus has to get into the labyrinth. And Theseus is courageous, but not very smart. So Ariadne gives him very detailed instruction. That he tells, you go and kill the Minotaur. And now you're going to get out. You don't know how to get out, but I'm going to give you a recipe book with just a small bounded number of recipes. Recipes being a certain succession of steps, meaning just, first multiply by this element of the set of generators and another, then another. And then no matter where you are in the labyrinth, at least one of these many recipes, these boundedly many recipes will work, will get you out of the labyrinth. The recipe book is blind, but one of these recipes will get you out of the labyrinth. And actually, the number of recipes and the number of steps in each recipe is not large. It's the same as before in the improved version. Yeah, and that's fantastic. Well, why is it fantastic? Well, because we are now in this situation where we are looking at the specific varieties that we need. And what's special about them is really that the conjugacy class is an orbit and T prime is an algebraic group, an abelian one. Well, how does that help? How does one usually prove dimensional estimates? So a simplified version without induction, without one kind of induction is the following. So yeah, this is the nicest sort of situation. When you have your variety and your say dim of G, the dimension of G is n and the dimension of V is m. And if you're lucky, no, the dimension of G is m and the dimension of G is n, say. Right? So this works out. And then if you're lucky, you manage to define a map consisting just of products, which takes this Cartesian product of m copies of V to a Cartesian product of n copies of G. So, and it could be something of the following form. It's usually more complicated, but it could be, V1 up to Vm, say n is m minus 1, and it could be that this map works. V1 times V2 inverse, comma V2, V3 inverse, and so forth. And then what you do, define B to be the intersection of A with the variety. And then you have, wishful thinking, the first step of a proof, according to Poya. So if phi were injective, generally it won't be, but say phi were injective, you have that ak to the n is at least as big as the image, because all of these products are in a to the k, in fact in a squared, or a times a inverse, and they are also in the image of this map. Now, if it's an injective map, the image is exactly as large as the domain, and this has size, this Cartesian product, the domain has size b to the m. Sorry, b here, this is outside. Number of elements of b to the m, and that's b is just intersection of a with v to the m. Right. So we get, just taking nth roots, the intersection of A with V is just going to be A to the K, the number of elements of that, to the M over K. All right. And that's just A to the K, number of elements, to dim V over dim G. Of course, phi is not generally injective, but even if phi were just m to 1, where m is reasonable, you would still get something like this. Just you would just have a constant of m in front. If m points get mapped to 1, then your boundary grades by a factor of m, which is fine if m is reasonable. Well, even that is not quite realistic. Realistically, you can define phi so it's generically m to 1. You can define it so the dimensions match. And if the dimensions match, then actually the result of Chevalier, I think, made explicit, tells you that generically, that is outside a variety of lower dimension, you are going to have that outside of the variety of lower dimension, the preimage of a point will have dimension 0, that is a preimage of a point, will be a set of points, and how many, that's bounded by the degree of the variety. All right, so, but that's a general case. That's why one of the reasons why you end up doing induction and your bounds degrade, unfortunately, because of induction. What can you do for CL of G, so the conjugate class of G, for T of G, and so forth? Well, because of Ariadne, there exist these elements in A to the K, such that one of these elements, no matter where you are, what your x is on V, on W, one of these elements multiplied by x gets you out of the nasty exceptional variety. And then what you get is that one of those copies works. So you end up having the bound of the sort you need, yes, with a factor of m in front. No big deal. And that really gives you the dimensional estimates you want for these particular varieties without a nasty constant in front. And that gives you the final result. Okay. So that's what we have shown. can we go further? We are still far from Babay's conjecture, and we are still far from what would be morally very close to Babay's conjecture, that is a result of the strength of my result with Sheresh for the symmetrical alternating group. Because a correct analog of that, so Babai would be log G to an absolute constant, and a correct analog of Helfgott-Sheresh would be log G to the to a power of log R, not of R. So we're very happy with our polynomial, but most likely it is possible to prove a result like that with a constant instead of a polynomial, or even if that's not the case, at least with log R to a small constant. So I think, it's just my intuition, that we will need to reuse some of the ideas that have been developed for the symmetric and alternating group for linear algebraic groups. But it's really not obvious how. I've been trying, and to some very limited extent, this has proved fruitful, but I think one should be able to go much further in joining the ideas from the two sub-problems. But I haven't got something there, and so it's a challenge to the newer generations and to myself. Now that we have got a polynomial exponent, what about a polynomial on log R? That would be beautiful. All right, so with that, I think I can finish.
Thank